Scapy. This tool reminds me of that song, any way you want it, that's the way you need it, etc. Because Scapy is a fantastic tool that can assist us in crafting virtually any packet that we want to. You need this layer 2 source address, you need that layer 3 destination address, you need these flags up at TCP, no problem. You tell Scapy what you want to put together, it does it on the fly for you, you hit send, and it injects that packet or packets into the networks. That's just the tip of the iceberg with Scapy. Let's begin. I'd like you to imagine that you and I are validating the configuration on a firewall. So here's the firewall. You can, in your mind, imagine whatever type of firewall you'd like. It could be Palo Alto, Cisco, Juniper, HP, doesn't matter. And let's go ahead and say this is the outside and this is the inside. And one of the policies that supposedly is implemented on this firewall is that it's not going to allow packets to a specific address if the source IP address is the same. For example, let's say we have a server out at 8.8.8.8, which would be a DNS server from google.com. And if a packet is ever going to that address, it should never have the same source address. That would be a malicious packet. So if the policy is in place, how do we validate that's actually functioning? Well, one way of trying to do that, and I've seen this done over and over again, is you take a PC and you give the PC the address 8.8.8.8, so the source address will be that, and then you try to ping that address. Now, what's the problem with that? Well, the reality is if we ping 8.8.8.8 from this machine, it's simply going to say, oh, that's me. It's going to respond. It's never going to go through the firewall. So we really haven't validated anything from a firewall policy perspective. One way of implementing this test is to use this amazing tool called Scapy. Scapy is very likely the most powerful and flexible packet manipulation tool inside of the Backtrack arsenal. It is written in Python, so we get to learn a little bit of programming in order to work with it. But check this out. Let's say we take a typical representation of the TCP/IP protocol suite. Up here at the top, we have the application layer, and then we have the transport layer. So the transport layer, we have things like TCP and UDP and GRE and ESP and others. And then as we go down to the network layer, we have IP and IP version 6. So I put version 4 or version 6. And then we have the data link layer. So on Ethernet, we're dealing with MAC addresses and the framing for that and everything else. And then down here, we have the physical layer. Well, let's say we wanted to craft that packet that we talked about just a moment ago with the same source address and destination address. By using Scapy, we can open up the command line interface, run Scapy, and we could create a packet. What layer 2 information do you want? You can specify virtually anything. Any source address, any destination address. At the network layer, what information do we want to provide? We can specify all the fields in the IP header, source address, destination address, type of service, everything else. We can specify literally what we want to include. If you're doing IPv6 and you want to verify, will RH0 header, will that really cause a problem on my network and blah, 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 blah. You can actually craft those packets. You don't have to find a program that'll do it. You've got a program that'll do it. Scapy will put anything you want at layer 2, 3, 4, or higher in the application layer. And then when you say send it, it will allow you to go ahead and send it. At the transport layer, if we want to find out, hey, I wonder what would happen if we sent a packet to this web server if we source the port from maybe the same port 80, or what happens if I set the flags in a certain way. So you wonder, how do people find out about these vulnerabilities on systems? They try various options and they find something that makes the server not know how to respond or respond incorrectly, divulge information, or blow up the protocol stack. We've just discovered a new vulnerability, and Scapy is an amazing tool that allows us to craft virtually any packet that we want to and then launch it out into the network. In addition to being able to create that perfect packet and play it on the network, it also has the ability to scan the network. It has the option of working with capture files, for example, from Wireshark. It also integrates with some graphical user interfaces for reports about what it's found. What you and I get to do right now is a demonstration of using Scapy at the command line, and here's what I've done. I've put the actual commands that I'm using that we're going to demonstrate together in the Nugget Lab download area, so you can go ahead and get started with Scapy. And then if you have a desire to learn more about it and work more with Python, there's a whole world of possibilities that can be done using this very, very powerful tool called Scapy. Our first step is to go ahead and run Scapy, Scapy, press enter. I'm going to run this on our little Raspberry Pi that's running Kali Linux. And we'd have a similar result, whether it's Backtrack or Kali Linux running on an Intel platform, because the functionality is going to be pretty much the same. I did get a little warning message about IPv6. That's not a problem because I'm not going to be using IPv6 for this demo, although I do want to point out that the current version of Scapy supports IP version 4 and IP version 6. There's not two separate tools that we have to use. We can use Scapy for creating packets for either one of those protocol stacks. Because there's so many possibilities with Scapy, let's go ahead and start with something fairly straightforward, and that's with the basic send command. The send says, go ahead and generate this packet. And here's the instructions that we're telling this packet to have. So for IP, we're talking about layer 3. We want to specify a source address and a destination address. The quotes represent that this group of information is all together. And we're going to be specifying we're using ICMP, and we're going to carry the text our payload inside of the ICMP packet. Now, are we specifying this is an ICMP echo request or a reply or an unreachable? No, we're not specifying the ICMP type at all. We're just saying it's ICMP and it's our payload. One of the very interesting things with Scapy is that we don't have to follow the rules. For example, could we make packets that logically would never be found on the network? The answer is yes. And by doing so, by creating malicious packets and throwing them at servers and devices, we can take a look at the responses that come back. And based on those responses, maybe we cause some weird abnormal behavior and discover a vulnerability in the process. So let's go ahead and launch this. Now, before I press enter and we launch this, let's go ahead and also bring up Wireshark also on this Raspberry Pi Kali Linux distribution. So we'll type in Wireshark here and launch that. That's going to open up in a separate window. So I'm using that X11 redirect back to my local machine running the X Windows server. And with that up right here, let's go back to this first window and let's start our capture on Ethernet 0. So I'll say start. It's going to start that capture. We'll come back to this in just a moment, and then we'll launch it. So we've just sent that one packet. Now, regardless of what our source IP address really is, it's going to use a source IP address of 192.168.1.55. That would be an easy way to spoof the source address just by telling it what you want that source IP address to be. So let's go back to the capture and take a look at the results. I let that run for a few seconds. There's like over 2,000 packets that it captured. If we want to filter based on this, we know that the destination we're looking for is 192.168.1.1. We can simply take the destination column, and you could scroll through it, I suppose. That'd be one way of finding it. But a faster way would be to right-click on this and say, I want to apply as filter and select that destination address. And then just go ahead after I select it here and change it up here. So instead of 19, we're looking for 1. It's still a valid filter. And then go ahead and click on apply. And that should show us only the packets with a destination address of 192.168.1.1, which is right here. So if we scroll this down just a little bit, so let's move this over just a little bit, and let's take a look right here. I don't know if you can see it very well, but right here in the output, it has our payload. So that was the actual payload inside of that ICMP message. And again, there's no rules. You can specify virtually anything you want to send out, and Scapy will be happy to do it for us. Another really good thing to be aware of with Scapy is how to get out, and it's Control D, as in I am done. Control D will take you out of the interactive command line interface, and that'll put you back at the command prompt for your Linux box. So let's kick it up a notch. We're going to run Scapy again. Previously, we worked with a single command to send a packet, but we can actually take additional variables and assign all the details for layer 2, layer 3, and layer 4, and then combine them all together and then send them out as one packet. The first thing I'd like to do is we're going to declare some variables. I'm going to create 3 variables, one called L2, and you can name them whatever you'd like, one called L3, and one called L4, and I'm simply telling the system that whenever I refer to the variable named L2, we're really talking about Ethernet. So all we're doing here, these are the variables I'm declaring, and I'm saying, okay, whenever I refer to L2, you know that I'm really referring to Ethernet. Whenever I say L3, I'm referring to IP, and whenever I refer to L4, I'm referring to TCP. And then as we start adding details, for example, we want to specify the layer 2 addresses involved, or layer 3 addresses, or layer 4 port information, we can refer to L4 as the variable, and it will know we're talking about TCP as an example. Just as a quick check, I'm going to type in L2, L3, L4, and it's simply showing us what those represent. So we said L2 represents Ethernet, that's what's shown here. L3 represents IP, and L4 represents TCP. Just to validate what our variables are representing. So what do we have so far? We've got something called L2, a label, if you will, a variable that represents Ethernet. We have L3 representing IP and L4 representing TCP. But what are the defaults inside of Scapy for Ethernet, for IP, for TCP? And to see that, we can just do an L2, which represents layer 2 Ethernet, and a show with parentheses and nothing inside of them. So this command right here says, okay, for Ethernet, the default destination address is a broadcast, and the source is nothing by default, and the actual Ethernet type is not set to anything specific by default. So we could manually set anything we wanted to inside of that layer 2 information. So for the type, for example, if an Ethernet frame was carrying IP, we would set it to hexadecimal 800, which represents, okay, the next layer up is IP. And it would be a different value for IP version 6. It would be a different value if it was 802.1q, etc. If we wanted to verify what the defaults are for IP, we could just say L3, that's our variable name, period show, and then parentheses, open and closed, with nothing in it, and that will show us all the details regarding IP. So IP is representing IP version 4, that's what that means. Type of service is not set, length, ID, flags, fragment, TTL, protocols IP, checksum is none, and then source and destination are simply the loopback addresses, again, by default. So what we could do is we could go in and specify any one of these fields inside of the IP header as we craft the quote-unquote perfect packet that we want to generate and send on the network. So we can manipulate anything at layer 2 and anything at layer 3. Before we start setting any of these fields to the values that we want to use, let's also go ahead and take a look at the defaults for TCP. So to see that, we say L4.show with a open and close parentheses. So L4 represents TCP. The show command is saying show us everything that's currently set. And here's the defaults it has for everything in the TCP header unless we specify something different. So if we want to change any one of these, we can. We can modify layer 2 information, layer 3 information, or layer 4 information. And the reason for changing any of these parameters might be just to validate a policy, validate that traffic is responded to correctly, or in an attempt to discover some vulnerability or abnormal reaction from a device when we send a specifically crafted packet. So let's work our way up the protocol stack. Let's specify a specific source MAC address that we want to use in a packet that we're going to send. So we're going to say L2, which it knows means Ethernet, layer 2. And we're going to say Ethernet, the source is going to be 0123456789AB. And that's the source MAC address we want to use for the packet we're going to send out. Now, is that a problem if that's not our real MAC address? The answer is it depends on the network. If the network is verifying layer 2 source addresses, and if that's not really your layer 2 source address, it could be stopped by the network. But many networks are not going to stop you if you have an additional MAC address. So from a switch perspective, it would say, oh, there's another source MAC address on this port. It would simply add it to the list of layer 2 addresses that are reachable off the port that your backtrack, or in this case, the Kali machine, is connected to. I'm a big believer in configuring something and then verifying that it actually took correctly. So how would we verify this layer 2 information? We use the same command we did earlier. L2, that's our variable name, .show, and then open and close parentheses will show us everything. And take a look. Previously, we had the broadcast address and we had all zeros here. And now it's specifically showing us that layer 2 address we specified right here that we want to use as a source layer 2 address. Let's do the same kind of treatment for layer 3. Let's go ahead and specify for layer 3, that's our variable name, that for IP we want the TTL to be 99. We want to go ahead and specify the destination IP address of 192.168.1.1. And then we can verify that that took as well by simply doing the L3.show, open and close paren. And that will show us all this stuff that's set for layer 3. And if you'll notice, this changed. What we specified was the destination, but it also is going to use our source address of this backtrack/Kali system as the source address by default when we specify a destination. And that's why it filled in both fields. If we wanted to spoof the source address, we could manually specify the source address here, and that would change the source from what our real IP address is as well. Again, that's how we create a specifically crafted packet that matched our needs for our testing. So let's say we made a mistake. We said, oh, that's the wrong destination address. How do I undo that? Well, we simply use the delete option. So delete and then in parentheses L3.dst. That will remove it. And if we want to put a new destination address back in, we can do so. And of course, it would be a great idea to validate that it actually took. Now, the part of deleting this I just did for demonstration, because if we specified a new destination address, that would actually overwrite the first one that was there. But I did want you to be aware of how you do the basic navigation of setting the variables and then deleting them if you don't want them, and then how to change them. For layer 4, let's also modify that. We'll specify that the source port is going to be 6783, and we'll specify the destination port is 22. We'll set a flag just for good measure. And then to validate that, we just use the L4 show again, like this. And there's our source port, there's our flag, and there's our destination port, just to validate that those 3 elements all got set. A quick way to validate what we did set. Now, we had a delete, we had some adds at layer 2, 3, and 4. To validate that, we just type in L2, L3, L4. And what it's showing us is the values we've set for each of the options within those variables. The source MAC address, the time to live, the destination IP address, the source port, the destination port, and the flags for each of the layers respectively. And again, you don't have to use the actual names of L2, L3, and L4. I thought that would just be nice and convenient to remind you of exactly what we're looking at. Before we send this packet off on its way, let's go ahead and start a brand new capture again. So I'm going to say I don't want to save the old one. I'm going to continue without saving. We're going to start the new capture. I'll minimize that as it's capturing. And let's go ahead and do a send. Now, a send is how we actually said that initial packet earlier, but now we want to send the L2, L3, and L4 information as part of the packet, and that packet has been sent. So in our wire capture, as we go take a look at it, we should be able to see the exact details that match our layer 2, 3, and 4 information on the packet that was sent. So in Packet Tracer, how do we find the packet with sorting through these 2,000 plus packets? Again, the easiest way is to put a simple filter on it. We'll right click on a destination address, say apply this specific destination IP address as a filter, and then go ahead and simply modify the filter and specify we're looking for 2 in this case, because that was the destination address. And then click on apply, and that should show us just the single packet. So if we open this up at layer 2, it should show us a source MAC address right here of 0123456789AB, which it does. That's fantastic. So there's our source MAC address right here. It should show us the destination IP address of 192.168.1.2, which is right here, which is perfect. And as we take a closer look at the TCP information, we should have a source port of 6783, which is right there, a destination port of 22 for SSH, and the flag should be set to A, which is right here for A for acknowledge, and we can actually open that up just to verify that as well. But it effectively says the same thing. There are a boatload of options and potential applications for Scapy. Let's go ahead and get out with a Control D. Again, that's how we exit. And let's go back in one more time. Let me show you one other option that I think you'll be interested in seeing, and that is using it as a sniffer. Some of the syntax inside Scapy, because it's written in Python, takes a little getting used to. But once you start working with it and you have some familiar commands you use over and over again, you'll be more comfortable from practicing with it. So what this command is saying, I want to sniff on Ethernet 0, and effectively, I want to show the output as it comes up. So anything that this interface sees, Ethernet 0, is going to be displayed to the screen. So let's go ahead and press enter. Now this, what we're looking at, is kind of a vicious circle because I have an SSH session open over to the Raspberry Pi running Kali Linux. So every time it sends information back to me, that's traffic. It has to report on that over and over and over again. So to stop this, I'm going to do a Control C. And that stops it. And here it has information on all the packets that it saw. So if we scroll up or down, it's going to show us the details. For example, here we have Ethernet header for this packet, and then here's the IP, and then we have TCP, and then it shows us for all the packets that this Kali box actually saw. It also has at the bottom, if we scroll back all the way down, it has a little summary. It saw 332 TCP packets, 4 UDPs, no ICMPs, and 1 other. Another way of doing that same sniff but not having it show all the details is to use the option of summary. So instead of x.show at the end, we put x.summary, and I'll put all these commands again in the Nugget Lab download area for you. So if we hit Control C now it's showing us how many packets it saw, what type they were, and it also has a summary of those packets that it displayed to the screen. There's also the really cool option of setting up a filter. So we can tell Scapy, you know what, don't just show everything you see. That's too much. Go ahead and only show it to me if it includes this item or the other, which is effectively creating a filter about which information is going to be collected by Scapy. So to set up a filter, it's really quite simple. We're going to use sniff again, and this simply use the word filter and say, I only want host 192.168.1.1. And the 5 says, you know what, only count up to 5. Gather up to 5 of these puppies. That's all I want to see. So when we hit 5, this is going to come back and tell us, hey, you've reached 5, and here's the results of it. So we're going to help it along the way a little bit. Let's just open up another window, and we'll do a ping over to 192.168.1.1. That'll help it. And I'm going to stop this ping, and let's go ahead back to our Kelly box, and there we have it. I had one TCP that slipped in, and I had 2 ICMPs and 2 others. So now the question is, okay, well, you saw that. That's very interesting. How do we go ahead and view that? And the way we're going to view that is we're going to ask for a summary. So we're going to declare a variable of, we use anything you want to as a variable. I'm going to use A. I'm going to say A equals underscore, and then I want to see a summary. And so here's my summary of those 5 packets that it captured. So here's our one TCP packet. It was part of an SSH session. And for the 2 ICMPs, that was right here. And then for the others, they were ARP, which I think is really interesting because the initial ARP request that went out, that's broadcast based. So as the broadcast ARP request goes out, inside of the ARP request, it specifies what IP address we're looking for. And this picked up on it as being a match. And as a result, that's why it made it into our first 5 packets from this request right here. If we wanted to take a closer look, which I really do actually, let's take a look at this guy. So that's packet number 1. So it's packet 0, 1, 2, 3, 4, which make a total of 5. If we want to see the details for packet number 1, we can simply type in A, which is our variable that we defined right here. So we'll say A, open bracket, number 1 for packet labeled number 1, close bracket, and that will show us the details for that specific packet. And here's the additional details on this packet right here, which is the initial ARP request. So it got broadcast out, the source MAC address was this, and inside of the ARP request, the request came from 1.55, the source MAC address inside the ARP request was this. We're looking for the MAC address of 1.1. We don't know the MAC address of 1.1, hence the ARP request. And the reply that goes back should have all 4 fields filled out. So we use an up arrow key and just swap out that 1 with a 2. This will be the ARP reply, and there's the actual ARP reply. In this video, we've answered the question, what tool could we call upon to create a maliciously or specifically crafted packet that we're going to put on the network? And my friend, Scapy can do that and a whole bunch more. I've had an enjoyable time with you in this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.